We'll pick up where we left off. We're going to be talking about hopfield networks and specifically Boltzmann machines today. So quick recap. We are familiar with what a hopfield network is. It's just a network, a loopy network where each neuron receives inputs from every other neuron and outputs to every other neuron. So when you actually set it at the connections are symmetric. In the basic form, the neurons are all binary threshold units. And anytime you set the network at some configuration, the whole thing is going to evolve to arrive at some stable pattern. We've seen this. We also saw that you can define an energy for the network, which by the way, can somebody actually check if the streaming's working properly? Just making sure. My TAs are not here. If someone can monitor PRZ, I'd appreciate it. Thank you. Right. So we also saw that we can define an energy for a hopfield network, which is basically a weighted combination of the product of all pairs of neurons in the network. And when the hopfield network evolves, it evolves to minimize this energy. So the overall hopfield network computation was something like this. You set it at some point, and the thing is going to at each point, each neuron is going to try to align itself with its local field, where the local field is simply the weighted sum of all of the other neurons. And these updates will proceed until the network arrives at some local minimum in the energy contour. And we saw that this is content addressable memory, that each of the minima in the energy contour is effectively a stored pattern. If the network is initialized close to a stored pattern, it's going to evolve into that pattern. So basically, you're recalling that pattern based on partial or corrupt versions of the stored pattern. So we saw some examples where we saw that if you had constructed a network to store specific patterns and you gave it degraded versions of the pattern, it would evolve to recall the entire pattern. There was one example where you gave it a noisy pattern. So the input provided now is a noisy version of the stored pattern, and it evolves to recall the pattern. In the other case, we saw where it actually performs pattern completion. You fix some of the bits, and you let the network evolve to fill in the rest of the data. We saw that it could do all of these, right? Now, so we saw that a hopfield network can be trained to remember specific target patterns, like the pictures in the previous example. And this can be done by setting the weights appropriately, right? Now, question, do you think you can train a hopfield network using backprop?
It's not a feed-forward network, and if you try to get up gradients, you will...
Correct. But on the other hand, if you think of this as a recurrent network, think of a recurrent network where you have input only at the first time and no subsequent inputs, right? So you can literally unroll this thing for a number of steps. Yes. And in that case, it just ends up looking exactly like a feed-forward network, right? So loopy networks can, in general, be unrolled, at least to fixed depth, to look like feed-forward networks, right? So now training the network here was the process of designing the weights matrix such that the energy of the target patterns is minimized, so they are in energy wells, and other untargeted potentially parasitic patterns have very high energy so that they don't actually become parasitic. They don't actually become fake memories. So the point of training the network was something like this. If the yellow dots represented states patterns that you would like to store, and if the current weight setting gave you the energy contour shown in the figure, then you try to update the weights such that the energy of the target patterns goes down and the energy of the remaining patterns goes back up, right? So, and for this, we could do this by trying to explicitly minimize the energy of the target patterns while minimizing the negative of the energy of the non-target patterns, which is the same as maximizing the energy of the non-target patterns. So you end up with an objective function like the one shown above, which has two components. The first component is the sum of the energy of all of the target patterns, and the second is the sum of the energy of all of the non-target patterns. So we would try to maximize the difference between the two, and just using your standard quadratic energy definition, the one given to the left, you end up with a simple gradient descent algorithm, in which case you would update the weights with a gradient term, where the gradient simply ends up being the difference between the sum of the outer products of the target patterns and the sum of the outer products of the non-target patterns, right? So it actually ends up looking a whole lot like Hebbian rule, the Hebbian rule where the first component is trying to perform a Hebbian update for the target patterns, and the second component is trying to push away from the patterns that you do not want to store, except it's not strictly Hebbian in the sense that some patterns can be repeated in order to emphasize the importance of their importance with respect to the other patterns. Now, so here is what the actual training algorithm did. The first component would be pulling down all of the yellow dots, and the second component would be pulling up the energy location at every other pattern. And so we spent some time focusing on what the second term is, because if you're trying to increase the energy of the non-target patterns, there's an exponential number of these guys, and clearly summing over the entire lot is not a feasible thing to be doing. So what we did was say, let's just increase the energy of the valleys. So instead of trying to pull up the energy everywhere on the energy contour, we figured it was sufficient to pull up the energy of the valleys, except that even in this case, the problem really was there can be an exponential number of valleys, and identifying all of them was not going to be feasible. So we made a compromise. We said we're going to pull up the valleys in the vicinity of the patterns that we are trying to store, which means that you would start off the network at the patterns you're trying to store, you'd let it evolve, and eventually the network would settle at some energy valley, and those are the locations whose energies you're going to try to maximize in the term to the right, in the highlighted term on the slide, right? So the overall behavior was something like this. You want to lower the energy at valid memories, so you want to pull down the yellow dots, and then you would initialize the network at each of these yellow locations, which are the patterns you're trying to store, let it evolve, and when it evolved, the network would settle at one of these points, and those points you would try to pull up through the second term in your in the update rule. So all this we've seen. Now, we also saw that instead of trying to pull up the valley itself, it's a little more conservative and possibly better to simply try to pull up the patterns in the vicinity of the stored patterns. So instead of actually trying to let the network evolve all the way to a valley and then pull the valley up, we said we can just let the network evolve for a few steps and then pull that location up so that you create valleys around the target patterns without potentially compromising other patterns. So all of this was a quick recap from what we saw in the last class, right? And so this gave us this update rule, which was if you are doing something like a stochastic gradient descent, at each iteration you would sample the target pattern, then you'd initialize the network at that pattern and let it evolve for a few steps to arrive at a down valley position, and then you'd update the weights with the difference between the outer product of the target pattern that you sampled and the outer product of the pattern that you arrived at after a few evolutions, right? So, and then we saw that you don't always necessarily get perfect recall. For example, over here, when you try to reconstruct a Bugs Bunny, you get this pattern to the right. And the reason for that is that you also have, for any pattern that you're trying to store, parasitic memories, local valleys which are not local energy minima, which are not things you're trying to store, but some spurious valleys that just happened as an outcome of the mechanism that you used to design the weights. And one way to try to escape these guys is to maybe add a little bit of noise, perturb the network once it settles at some point, and then go back and let it evolve again. So if you perturb the network, if you happen to be at a local minimum, then a perturbation is likely to get it outside the local minimum, and then it will continue down into a deeper valley. So this is a very simple standard technique that we often use in such systems to actually get to a better optimum. And to do this, and here's where we left off, we saw it makes sense to think of the Hopfield network as a distribution. So we actually presented this as from a second perspective. We also saw that defining the machine as a probability distribution, the Hopfield network, potentially allowed us to store the n memories more robustly and possibly even store more than n memories, right? So the way we did that was that we made the network stochastic, and now we said that the system is not deterministically in any particular configuration. It's stochastically in a configuration, and we'll see exactly what this means in a few minutes. So with respect to, now all of this was based on the equivalence to thermodynamic systems. We saw that, right? So for any configuration, you can define an energy, E of S. This is basically the energy of the Hopfield network, except now we say that the probability of finding the system in any configuration S is proportional to e raised to minus the energy of S, which is the same as saying that minimizing the energy is the same as maximizing the log probability of the state. So we haven't really changed anything in terms of the actual objective that you would be trying to optimize when you let the network evolve. You'd be essentially letting the network evolve towards more probable states as opposed to lesser energy states, but these two are strictly equivalent to the manner, given the manner in which we have defined this probability distribution, right? This probability distribution is what we call the Boltzmann distribution, and this is called the Boltzmann distribution because we arrived at it based on the equivalence to thermodynamic systems, where the Boltzmann distribution actually defined the steady state probability distribution over the states of the thermodynamic system, right, at equilibrium. Now observe that this can also now be viewed as a generative model. For example, if you just randomly let the network evolve, and then you started off at some point and let the network evolve, and it finally arrived at some configuration. If you repeated the experiment many times, then if you did things right, then the probability distribution over states that you would find, you would expect it to follow this particular distribution, right? Again, going back to this, if you actually let the system, if you scan the all possible states of a Hopfield network, then and you select them based on the probability distribution that you've given here, that's going to affect that's again equivalent to generating samples from that distribution, right? So what exactly do we mean by letting the network evolve according to this probability distribution? So what do we mean by generating samples from this probability distribution? To see that, let's first consider 2-bit patterns. two configurations which differ in only one bit, right? So let's say I have a pattern and I'm considering only the ith bit. Now the ith bit can either be +1 or it can be -1, right? So the probability of the entire sequence is the probability of all the bits except the ith bit times the probability of the ith bit conditioned on everything else, right? So, and that can if the two variants of the pattern are, one is with the with the ith bit, one is if one is +1 +1 +1 -1 -1 -1 +1, whatever. The other one is going to be exactly the same thing, except that one specific bit will be different and everything else is the same. So we are looking at two variants. This is S, this is S prime, right? So you have all of these bits which are common to both. So these are the j not equal to I bits. And so the probability distribution, the probability of this entire pattern is the probability of these regions times the probability of this bit given the rest of the bits, right? So the probability of the entire pattern is the probability of all of the bits except the ith bit times the probability of the ith bit given the rest of the bits. So these terms are, none of these pens, right? So these terms give you P of S j not equal to I, and this term is P of Si given S j not equal to I. The product of these two is going to give you the product of the entire sequence, probability of the entire sequence. And this ith bit can take two values. It's either +1 or -1. So for the probability of the two patterns is P of Si equals +1 given the rest of the bits times the probability of the rest of the bits, and the probability of S prime, which is the same as the SS but with the ith bit having a value -1, is P of Si equals -1 given the remaining bits times the probability of the remaining bits. Now if I take the difference in the log probability of these two patterns, mind you, I'm just looking at the difference in the log probability of two patterns that differ in only one bit, right? That is going to be, if you just work it out, simply this is basically the probability of the log of the ratio of these two probabilities, right? Log of PS minus log of PS prime is the same as log of PS divided by PS prime. But then PS prime is simply 1 minus PS, because between S prime and S, right, there's a difference of 1 bit. So if I'm considering only the ith bit, the ith bit can either take a value +1 or -1. This additional term, the second term, cancels out. Sj not equals I cancels out. And so in the numerator and the denominator, you're going to get the probability of the ith bit given the rest of the bits. The probability the ith bit takes the value +1 given the rest of the bits, divided by the probability the ith bit takes the value -1 given the rest of the bits. So this denominator is simply 1 minus the numerator. So I can actually write this log probability in this manner, right? And if you actually work this out, what is that term? Remember, the log probability of any pattern is simply the energy for that pattern, right? So the log probability of the pattern with the ith bit set to 1 is going to be the energy from the contribution of all of these bits plus the energy from this one bit. And the energy from this one bit is that bit value multiplying the field. So I can write this as the contribution of all of the bits that are not I plus the ith bit times the local field. And the ith bit can take either the value +1, in which case its contribution is going to be plus the local field, or the ith bit can take the value -1, in which case its contribution is going to be minus the local field, right? So if I take the difference between these two log probabilities, this first term will cancel out, which is the contribution of all of the other bits, which is the same for both patterns. And all that remains is going to be the field at the local bit. So this has, it looks a little bit complicated, it's not very, but here's the really nice nice result that comes out of it. If I take the difference in the log probabilities of these two patterns, which only differ in one bit, that simply ends up being the field at that bit. So if you work it out, it turns out that the probability of the ith bit being 1 given all the remaining bits is just a logistic. It's a logistic computed where the argument of the logistic is the field at that bit, which is simply the affine combination of all of the other neurons given all of the affine combination of all of the other neurons for that pattern. So now it turns out that although we started off with a hopfield network, converted it to a probabilistic machine and worked our way backwards, we ended up with exactly the same kind of activation, the same kind of behavior that we've been seeing in traditional multi-layer perceptrons, right? So, which also explains why even MLPs can be thought of as giving you some kind of a posterior probability for the pattern, right? So here's how we can now redefine the network. You can define the network as a regular hopfield net. Define the regular hopfield net as a stochastic system, but now each neuron is a stochastic unit which takes the value 1 with a probability that is simply the logistic computed at that neuron. So I'm going to say, instead of saying +1 and -1, I'm going to use the notation of +1 and 1 and 0, which is the more traditional binary representation. It doesn't really change things very much. This is just convention, right? So here's how I can think of the hopfield network as a distribution. It's a probability distribution over binary sequences. It's a Boltzmann distribution. The conditional distribution of the individual bits is a logistic. And so if I want to evolve the system, what I would do is I'd initialize the system somehow and then cycle through the neurons. And for each neuron, I would compute the local field. I'd compute a logistic over the local field. That logistic can now be thought of as a Bernoulli variable. It's like flipping a coin. And I'm going to flip a coin with a probability of heads given by this value. And if the coin comes up heads, I'm going to set that bit to 1. So basically now I can probabilistically set each value to 1. This is very much like the hopfield network we saw earlier. Earlier we saw that if changing the value of the bit reduced the energy, you flip the bit. Now if you're going to make it more probabilistic, if flipping the bit is going to reduce the energy of the bit, you won't always still flip the bit. You're going to flip the bit with some probability. You're going to decide whether you're going to flip the bit or not based on this logistic probability distribution, right? So this you can now do. You can keep cycling. So when I speak of sampling the hopfield network to obtain a specific pattern, what it means is that I'm actually going to start the network at some pattern, and then I'm going to cycle through all of the neurons, and each neuron is going to be set according to this logistic probability. And if I keep repeating this, eventually the network is going to settle at some configuration. So this is going to be one sample drawn from the network. And what I mean by saying that the hopfield network is a probability distribution is that if I repeated this process many, many times and sampled many sequences, the distribution of that sequences is going to be the Boltzmann distribution. So a quick recap over here again. The hopfield net is actually just a probability distribution where each bit is set to 1 or 0 according to a probability, which is the logistic computed at that bit, computed over the affine combination of that bit, yes.
So when you fix the n-1 bits, do you sample all of the remaining bits just once?
So basically all we are saying is I initially initialize the network, then I go to each bit, and based on the affine combination of the other bits, I decide whether I'm going to flip it or not.
And then just once, right?
No, I can keep repeating it. Then I go to the next bit and repeat the process, and I keep looping through the network continuously.
But then do you fix other bits as well?
So every time I'm sampling one bit, the rest of the bits are fixed.
Oh, I see.
Right, so I can keep looping through it, and all the bits will eventually change.
You update the bits iteratively.
Yes.
Not like the entire weights
Yeah.
together.
Yeah. So I mean, I can just keep flipping the bits. I can randomly choose a bit, decide whether I'm going to flip it or not, and then go to the next bit, and I repeat the process. Yes.
Wouldn't the ordering matter?
It's stochastic, so yes, it would matter in the sense that the order in which you do it is going to change the final outcome that you get. All you're guaranteeing is that eventually the bit sequences that you get when the thing converges are going to be samples from the Boltzmann distribution. That's all.
So like, yeah, order is going to matter in what changes, but in the long run,
Yeah.
that order is going to just kind of...
Exactly. Exactly.
But can you also like compute the probability first, then flip every point like together?
We could do that. The point is, you could do this again. If implementationally, you could be doing this in batches, or you could be doing this one bit at a time, right?
The order doesn't matter because you
Yeah,
are updating everything.
that's correct. Exactly. So now here's where we started off in the last class by finding the equivalence with a thermodynamic system. A thermodynamic system has the notion of a temperature. So this was one of the other brilliant pieces of innovation that Hinton came up with when he began working on this, which was that when he reintroduced the notion of he invoked Metropolis Hastings and reintroduced the notion of temperature. When you compute the field, the affine combination at any neuron, in the basic framework, you just computed a logistic on this affine combination. Instead of computing just a logistic, now you can also multiply the z by 1 over t, where t is a temperature parameter. If the temperature parameter is 1, then this is the standard hopfield network. But then it can be something other than 1. And by introducing this temperature, it actually gives you the ability to slide between a hopfield network and a Boltzmann machine, where the Boltzmann machine is the stochastic machine and the hopfield network was the deterministic system, which always evolved towards the lower energy configuration. So this first term over here quantifies the energy difference obtained by flipping the current unit. Right? That is the field, right? If the difference is not large, then the probability of flipping a bit approaches 0.5. So if the difference in energy between this configuration and this configuration is effectively 0, the difference in the fields at this neuron for these two configurations is 0, then it doesn't matter what the value of that neuron is. The overall energy of the system is going to be the same. And so now the probability of flipping the bit is going to become 0.5. On the other hand, if flipping the bit is going to greatly increase the energy, that means z becomes a very large value. The probability of flipping the bit becomes 0. If on the other hand, if flipping the bit is going to greatly reduce the energy, the probability of flipping the bit becomes 1. And for intermediate values, you're going to get a value between 0 and 1, right? And finally, this temperature bit gives you this control. If I increase the temperature and make it infinity, then the bits are all flipping randomly because z is always 0, so the logistic is always at 0.5, and you're flipping the bits according to this logistic. On the other hand, if temperature is 1, you get the basic Boltzmann machine that we just saw. If the temperature is 0, you're only going to flip if the energy decreases. This just becomes the deterministic hopfield network. So by introducing this temperature, you actually give yourself a sliding control between deterministic and stochastic behavior. And now you can use this temperature to actually escape local minima. And the way you would do it is that here's how the hopfield network evolved, right? at each bit, you checked if flipping the bit reduced the energy. If it did, you flip the bit. Wait, I have lost a slide. So what you will do now is to set the temperature at some high value and then begin letting the network evolve. And then if you reduce the net temperature slowly enough, eventually the network is going towards zero. Then eventually the network is going to arrive at deep valleys and not get stuck in local minima, which means that the patterns that it recalls are much more likely to be valid memories than bogus patterns, right? So here is the, I'm missing the temperature bit over here, right? So if the temperature was set to 1, this was how your hopfield network, the Boltzmann machine, would evolve. You're going to be looping through the network, the neurons, and you're going to be flipping each neuron according to a binomial probability, which is computed using the logistic, right? So a couple of questions. If I'm going to let the system evolve, how long do I let it evolve? When does it stop? And secondly, if the network is continuously evolving, what exactly do I mean by the current state of the system? Because the bits are always flipping, right? So there's no notion of a current state of a system, because anytime I look at the system, the current snapshot is going to be different from the snapshot one instant from now. So the network is always changing. So here's how, if I'm trying to recall a memory, then we need to have a much cleaner notion of finding the current state of the system, the final state of the system. The system has evolved, there's a final state. Here's what we'd do. We'd let the system evolve to an equilibrium. What I mean by letting the system evolve to an equilibrium is you let it evolve for a very long time, and then eventually, when you actually look at the system, you can trace the system through a certain number of evolutions, say L of these. And so after L evolutions, you're going to find L different configurations for the system. And you just average these L configurations and take the sign of the average, and that's going to give you the final stable state of the system. That would be the recalled memory. So you're taking the expected state of the system rather than the actual observed state of the system, and the expectation is obtained by letting the system evolve for a bit and then taking the average, right? Now, and here's where this business of annealing comes in. This was another of so the slide was there. Right? This was another of Hinton's innovations, which is that instead of letting the system just evolve in a fixed manner, you start off by having a very high temperature value, so that the bits are much more likely to flip, and then slowly let the temperature come down to 1 or even go down to 0. And then when you do that, you can actually show that if the temperature goes down slowly enough, then you're guaranteed, with a probability approaching 1, of finding a pattern, finding the lowest energy pattern for the network. So you're guaranteed to find the global minimum. It's in practice, you're never going to let the temperature go down very slowly, but you're nevertheless guaranteed to find a local minimum. So for different kinds of behavior, let's say you want to clean up a noisy pattern. You're trying to recall a memory, but then you have a noisy version of the memory. Then you'd initialize the entire network with a noisy pattern and let it evolve. On the other hand, if you have a partial memory, like when we had the picture of the chipmunks with the lower portion wiped out, then you're trying to perform pattern completion. In that case, you would fix the portion of the network that represents the portion of the pattern that you do know, that you're certain about. And then you let the rest of the network evolve. And then when it settles down, you would actually have the recall memory, right? So, questions?
Here, each time we will update all the states for each cell.
Yeah. All of the states are the states. If you're doing a pattern completion, you wouldn't be updating the states which you fixed.
I mean, in each iteration, you will update all the cells.
In each iteration, you'd be updating everything that you want changed. So, for example, if you're trying to recall the chipmunk and you have the upper portion of the picture, those cells are not going to change. Those are fixed. Their values are known. So what you're really doing is finding the most likely value for the remaining bits conditioned on the pattern portion of the bits that you actually saw, that you're actually aware of. So you can actually show that this is a maximum a posteriori estimator. The Boltzmann machine now ends up being a probability distribution. And specifically this act of pattern completion is going to say, let's say I have a pattern S, which I can break down into S1 and S2, and say, let's say this is the chipmunk pattern that you did see, right? This is the partial chipmunk pattern. And then, so this is the unknown portion that you're trying to fill up. So when you let the network evolve, and then you compute this guy, what you're really doing is you're trying to find the portion of find the bit pattern for the remaining bits that is most likely given the portion that you do know. So it's a maximum a posteriori estimator, or if you're averaging, it ends up being a minimum mean squared error estimator, right? You're using the probabilistic interpretation of the same network to get a statistical estimate. So now, we spoke of letting the network evolve, but how do we know that it's actually arrived at some kind of a stable state? How do we know that it's actually maybe it's time to sample the output? And for that, of course, we have to go back and look at the probability distribution. And it's very trivial to show that if you actually think of each neuron as following a logistic, then the probability of distribution for the entire configuration is simply given by the Boltzmann distribution. So I derived the logistic for the individual neurons by going back from the Boltzmann distribution. You can close the loop by going forward and say that each of these neurons has a logistic probability. And then if you compute the joint probability of all the neurons, you're going to go right back and you will end up with the Boltzmann distribution, except that you actually have the Boltzmann distribution. And the Boltzmann distribution, you have E of y divided by t, which is much closer to the original thermodynamic definition than when we first set the t to 1, right? So if for any given value of t, you can show that the probability distribution for the entire bit sequence is the classic Boltzmann probability Boltzmann distribution with the Boltzmann constant set to 1. So the Hopfield net is a binary distribution over binary sequences, is a Boltzmann distribution, and the conditional distribution of the individual bits in the sequence is a logistic. We're going to call this whole thing a Boltzmann machine because it's implementing the Boltzmann distribution, right? And of course, we can view this whole thing as a generative model, which has a probability of producing the probability of producing any binary vector y is given by the Boltzmann distribution, right? What we've seen so far is how, given a weight matrix, how do you let the network evolve to recall a pattern? But the reason we started off with this whole process of defining this as a statistical machine was to try to be able to learn these weights so that you could store patterns more effectively, right? So let's go back and look at how exactly we would learn the weights. How do you train the network? Now, for training the network, you must learn the weights to remember target states, or basically, and to dislike non-target states. In other words, you wanted to assign a very high probability for the memories that you do want to store, and you wanted to assign a low probability for the stuff that you do not want to store, right? So basically, we want to be able to say that once we think of it in terms of assigning probabilities, we can think of the whole thing in terms of likelihoods. You must train the network to assign a desired probability distribution to states, meaning I wanted to assign a high probability to things I like and a low probability to things I don't like, right? So you can think of the act of memorization as training this distribution. You're given a set of training inputs, S1 through SP, I'm calling it S now because the state of the network. And if I give you a large number of training inputs, I want the network to assign higher probabilities to patterns that I've seen more frequently, lower probabilities to patterns that I've seen less frequently, and even lower probabilities to patterns that I haven't seen at all. So this is my way of creating a probabilistic machine that stores the kind of patterns I want, but at the same time it's also a probability distribution which naturally assigns greater probabilities to things that I have actually seen. So now you can think of the whole thing as maximizing the likelihood of stored patterns, and we can apply maximum likelihood training. So now first look at the probability assigned to any pattern. The probability assigned to any pattern is e raised to the negative of the energy for that pattern divided by a normalizing constant. And the normalizing constant is simply the sum over all possible patterns of e raised to the negative of the energy for the pattern. So the denominator actually sums over an exponential number of patterns, right? Because the denominators, that's got every possible pattern that the network can possibly store. So when I compute the log likelihood for this for any given training pattern, the log likelihood is going to have two components. The first one is simply going to be the negative of the energy for that pattern. The second one is the log of the summation over an exponential number of patterns of e raised to the negative of the energy for the pattern, right? So that the log likelihood for any given pattern has these two components. The first one to the left within the parenthesis is simply the energy for the pattern, because we know that the probability of any pattern is proportional to the negative energy, right? But the second term is the normalizing term, and the second term, the partition function, which is what is the bothersome bit. Now if you actually want to optimize this guy, this means that you not only have to increase the first term, you have to decrease the second term, and if you want to decrease the second term, you have to consider all exponential number of combinations of this second term, right? So, and this is going to be for one pattern. If I'm training over a large number of patterns, I will be computing the average log likelihood over many patterns. So I'm just taking, which is the term highlighted in yellow. So now, if I want to perform something like gradient descent, I'm going to have to compute the derivative of this log likelihood with respect to every term, right? Now consider the derivative of the very first term with respect to any wij. The first term is simply comprises wij times the product of bits. So when I take the derivative of the first term with respect to any wij, the wij goes away. All you are left with is the average of the product of the bits on either end of the connection between neuron I and neuron J. Wij basically is the weight that connects two neurons, right? So the first term simply ends up with this average product. It begins to look a whole lot like the Hebbian rule. The second term, that second term is the problem, because if you actually work out the second term explicitly, you're going to end up with this, the derivative of an exponential sum. But let's actually try to work it out. So here is the second term. The second term is the derivative of this summation over an exponential number of patterns of the exponent of the negative energies, right, with respect to wij. But then what is the derivative of the log of any term? It's going to be the derivative of the term divided by the term itself, right? So when I take the derivative, that's going to this guy. I wish I had my pointer. So the numerator term over there is first going to end up in the denominator. You have I have the derivative with respect to wij of the log of the summation over xpof minus energy of S prime, right? This is the term that I have. And this is going to be 1 over summation S prime of xpof minus the energy of S prime times the derivative of negative of the times the derivative S prime with respect to ij. Right? This is just a standard derivative rule for the logarithm. And this term over here is going to be actually derivative of x, right? And this term in turn is going to be the exponent of e of minus s, and then I have this term left over, which is summation s prime xpof e of minus s prime, and then finally the derivative with respect to ij of e of s, right? So if I just work the derivative out in 2 steps, and I'm just going to end up with the term to the right, and this is the summation over all s prime terms, because each of them is, wait a minute, this is s prime. And this over here is simply the probability of the pattern itself. So if you work your way through the arithmetic, it simply ends up being the expected value of the product of the bits, ith and jth bits, over the entire distribution, the second term and the gradient. So my arithmetic here is perhaps not very clean, but the slide says it all, right? So when I actually look at the gradient descent rule, the gradient descent has this term, the first term to the left is going to give me the average product over all the patterns that I'm trying to store, and the second term is going to give me the expected value of the product over the entire distribution. And once you realize this, then the problem becomes simple. When I'm trying to compute an expected value, and if the expected value requires a summation over infinite terms, what is the most standard way of coming up with an approximate estimate for the expected value? You do this through sampling, right? If I'm trying to compute the expected value of a random variable, the way I would do it is to sample the probability distribution of the random variable and take averages. So that's what we're going to do. Instead of explicitly computing this expected value, we're actually going to simply sample the distribution. And we've already seen what it means to sample a Boltzmann distribution. You just set it at some value, and you let it evolve. And if you do this repeatedly, every time it converges, it's going to give you one sample from the distribution, right? So you initialize the network randomly and let it evolve by probabilistically selecting state values according to our model. And then after many epochs, you just take a snapshot of the state. You do this many, many times. So I'm going to call this a simulation. Yes?
When it's a snapshot, do you mean like before when you talk about taking a long time?
No, just one snapshot. Earlier, because we were trying to take an expectation, right, at the configuration, right? Just take one snapshot. And so each time you take a snapshot, it's going to be at some state with some probability, right? And so you take many snapshots, and each of these is going to be what I call a simulated sample, which is basically a sample drawn from the probability distribution. And then I'm going to say that my derivative of the denominator can be approximated as the average of the pairs of bit values computed over all of my snapshots. It's an empirical estimate for the expectation that you have in the upper term, right? So this is the average of sample states when the network runs freely. And so overall, if I'm trying to compute the derivative of, if I'm trying to compute the derivative of the log likelihood of a training set, it's simply going to be the difference between the average product of pairs of samples computed over the training set minus the average product of the same two samples computed over all of the samples that I've drawn by randomly sampling from the distribution. But the arithmetic, again, it's very straightforward. And the reason we went through all of this effort of trying to understand the Hopfield network is that when you go back and look at all of this arithmetic, it basically gives you the same thing that you saw for the Hopfield network, which is intuitively very, very pretty and somewhat clean, right? So the overall training is going to be something like this. You would initialize all of your weights. You let the network run to obtain simulated state samples. And then you compute the gradient as you have in the formula above for each weight, where the gradient is the difference between the average product of the bit values on the training set minus the average product of the bit values computed on the samples, and just use your standard gradient descent, right? Gradient-based update rule. Now, observe that this is very similar to the update rule for the Hopfield network, right? This is pretty much what you're saying is that you're using, in fact, exactly the same as the Hopfield network update rule. So after all of this rigmarole, what did we end up with? The same update rule as the Hopfield network. The only thing that changed was the manner in which we selected these other guys, the negative samples. As far as the positive samples were concerned, you had exactly the same component. So you use this stochastic machinery to decide which negative samples you're actually going to use to update your Hopfield network, right? So so what was the point of all of that then? Why do I have to go back and define everything in terms of a deterministic, in terms of a stochastic machine, convert what was a very nice, clean content addressable memory to a probability distribution, and then talk about sampling it, etc., when I could have just gone on and just used the original procedure for Hopfield networks and come up with essentially the same kind of update rule? That really comes in when we now talk of expanding the capacity of the Hopfield network. And we've already seen how you can expand the memory capacity of a Hopfield network. We saw that if you're trying to store n bit patterns, you can store at most n of these patterns with any reliability. So if you want to store, if you want to store more than n, then what we did was to append a bunch of don't care bits. And then once you appended a bunch of don't care bits, if you had appended k bits to the original n bits, now the capacity became k plus n. And so you could store more patterns. But then in the process, you also learned a more complex probability distribution. So to expand the network, we add a large number of neurons whose actual values we don't really care about. And so if I add k bits, the new capacity we saw was n plus k bits. Although we are only interested in the values taken by the first n bits. We don't really care what the remaining k bits are. Yes?
So does that mean we don't, we're still training the weights between all of the other k bits, right?
We are training the weights for all n plus k bits. Right? Now you just accept that you are focusing on the n bits as far as your recall is concerned. So we are interested in n bit patterns. And the terminology we introduced was the bits that we were interested in are the bits we're going to look at. So we're going to call them the visible neurons. And the ones that we don't care about, their value doesn't really matter. So we call them the hidden neurons. So the neurons that store the actual patterns of interest are the visible neurons, and the ones that only serve to increase the capacity of the network but are not otherwise important are the hidden neurons, right? They can be set to anything in order to store a visible pattern. And so now, if you expand the capacity of the network in this manner, for a given pattern of visible neurons, there are any number of hidden patterns. For a single visible pattern, I can generate up to 2 raised to k hidden patterns, right? Which of these do I really keep? So ideally, you want to keep the k-bit pattern, which results in the lowest overall energy for the n plus k-bit pattern. But then that's going to be hard to choose, considering the weights themselves have not been set. And the search space is exponential on k for every single visible pattern that you're trying to store. And we saw that in the process that, in fact, we could have stored multiple hidden patterns coupled with any visible pattern. And these would be multiple stored patterns that all give the same visible output. And once you realize this, you say the natural question is, okay, for storing any particular pattern, how many extended patterns do I really store? And in fact, do I even need to specify how many patterns do I store? How do I just say, okay, let me consider every possible pattern that I could have for this visible pattern? Now, when I say every possible pattern, I'm suddenly blowing up the space again, right? So what exactly do I mean by this last bizarre statement? For that, we go back and look at the Boltzmann machine without hidden units. When you consider the Boltzmann machine without hidden units, it's the same thing. You can store up to, you can control the position of up to n local minima in the energy, or you can control the position of up to n local maxima in the probability distribution. The rest you have no control over, or at least not very much. But then, now you can extend this to have hidden units like so. And now with the hidden neurons, the complete state pattern, what happens is that the complete state pattern for even the training patterns ends up becoming unknown. Because you only know when I give you some training samples, I'm only giving you the training samples for the visible neurons. I'm not giving you the training samples for the hidden neurons, right? And so then how exactly do I go about the process of training? We can invoke maximum likelihood training. We can explicitly, the nice thing about the probabilistic definition of the network is that you no longer have to specify what the hidden neurons are. You can explicitly say, I don't care what they are. Store this visible pattern. And what exactly do I mean by that? I can think of an extended pattern as a combination of the visible bits and the hidden bits. So the hidden bits are what we'll call the latent bits, the bits that are not seen. Their job is to support the visible bits. And now, if I want to compute the probability of any particular visible bit pattern, I can simply marginalize out all the hidden values, right? And so by marginalizing out this process of marginalization has this natural characteristic that it's going to focus more on hidden patterns that are more likely and less on hidden patterns that are less likely. So in effect, you're focusing more on hidden patterns that have lower energy and less on hidden patterns that have higher energy and are really unlikely to affect the behavior of your network. So again, this summation is still over an exponential space. But anytime you think of a summation, what are we really doing? When I'm summing over all of P of V, I'm basically taking the expected value of P of S, of P of V, after having over all possible hidden values, right? So you can sample. You can repeat instead of explicitly summing over all of the terms, you can actually just sample. For each training pattern, you can let the hidden neurons evolve, and each time it evolves, it's going to give you a hidden pattern. You take a snapshot, I get one snapshot of age, so I can append the snapshot of the hidden values to the visible values, I get a completed pattern. So for each visible pattern that I'm trying to store, I can repeat this process many times. And I can generate many extended patterns, and I'm going to get different extended patterns different numbers of times based on their probability, right? Things that are more likely will occur more frequently, things that are less likely will occur less frequently. So now I can generate synthetic extended training data where I have many clones of the visible pattern that I'm trying to store, but the hidden values will all be different. So I have many different versions of the visible pattern I'm trying to store, all of them extended in different ways. So now, if I want to compute the overall behavior of the network, that is the behavior of the network when I think of the whole thing, visible and hidden patterns, as one combined unit. So I can just unclamp the visible units. I no longer fix the visible units. I let the entire system evolve. And those things are going to give me a different bunch of samples. So this is a different set of simulations. So I have two sets of simulations, one where I fix the visible values and let the network evolve, the other where I let the entire network evolve. And now the gradients can simply be computed over these two sets of terms. So the first term over here now is computed over the completion of all of the visible patterns. So the first term 2 is being derived from from samples, but these samples were derived fixing the visible patterns. The second sample is derived over the entire network, but otherwise this behavior is exactly the same as what we had before. So yeah.
So in the second term, do you just randomly initialize visible and hidden?
Yeah, or you can just unclamp the visible units and let them evolve. So you get something that's close to the visible units.
Okay, so you're keeping the initial hidden states that you found in the first set, like when you fixed the hidden, fixed the visible and got the hidden, you're then using the hidden.
You're not, no, I'm not, so then I can, I fix the visible and got the hidden, then I initialize the visible and the hidden randomly. But the visible could just be the training patterns I'm trying to store. And then I let the entire network evolve. So that way you're still getting these samples which are in the neighborhood of the visible patterns.
Sorry, how are they in the neighborhood of the visible patterns?
In the sense that if I have a pattern, I have these visible patterns of visible bits here, I have the hidden bits.
Yeah.
Initially, I clamp this, and I let this guy evolve, right?
Okay.
Subsequently, I unclamp it and let these change as well, and I let the entire network evolve. So when I let the network evolve, it's sort of trying to go downstream, but in the vicinity of a visible pattern, right? But that's, again, these are all engineering. It's engineering beyond a point, and there's some, but you get the idea, right? Yes.
The second term is supposed to be like a random sample of the entire states, right?
The second term is supposed to be a random sample.
So you should randomize the entire thing and don't
Yeah.
care if it's hidden or not.
Yeah, but simply given the large exponential number, in practice, this is what we really do. So now we're actually going right back to sampling in the vicinity of the visible patterns.
So
That's
a random sample you
yeah,
choose to those.
yeah.
Just want to raise the neighborhood.
Just again, you're raising the neighborhood. That's all it is, right? So you want to make sure that what you're really trying to do is to make sure that the likelihood of your visible pattern is maximized with of the training instances is maximized with respect to the other guys. And there are problems with this, right? If you think of it in terms of a probability distribution, now this is what is normally done when you train Boltzmann machines. But think about this. When you're learning a probability distribution, if some pattern is highly likely, the general assumption for probability distributions, for learning probability distributions, is that the distribution is smooth in the vicinity of the training instances, right? And here you're doing the exact opposite. When you train Boltzmann machines, you're sort of making this peaky in the vicinity of the at the training instances, and you're trying to push the neighborhood down. So this is somewhat of a counterintuitive thing that's done in this particular setting. But the only way to really explain it is to sort of map it back to hopfield nets. Yes.
So is the goal then to have a training set that's very evenly distributed, and you have lots of training data so that
No, though you want a training set that actually represents the patterns that are highly likely, right? So in theory, so there's this issue with training Boltzmann machines, and this is one of the reasons that we try to the whole Boltzmann machine formalism is not as popular as just thinking simply, working simply with feed-forward networks and multilayer perceptrons. Is that the training process is in some way backwards. Think of training a Gaussian. If I give you if you train a Gaussian distribution, what really happens? If I give you a bunch of training points, you try to make the vicinity of these training points all highly likely, right? Here you're doing the exact opposite. You're taking some training instances and you're trying to push down the stuff in the neighborhood, and it's a bit of a it's somewhat counterintuitive, at least to me, right? So here's what we ended up with. Boltzmann machines are stochastic extensions of hopfield networks, which enable storage of many more patterns than hopfield nets, but also enables computation of probabilities of patterns and completion of patterns, right? So here's the overall framework. Training, you'd be given a bunch of training instances, which could be repeated to represent relative probabilities of different patterns you want to store. You'd initialize your weights. Then you'd clamp the visible values, the patterns that you're trying to store, and you let the network evolve. And you get a bunch of training samples. Then you unclamp it and let the network evolve. You get a bunch of other training samples. Compute the gradients and update the weights. And yes?
Yeah, so I should have asked this question earlier, but like I still don't get the idea why adding the hidden neurons can increase the capacity if we do not care their values.
So we know that if you have n plus k bits, you can store n plus k patterns. Right?
But like, I thought we were trying to train the model to memorize only the visible states. Right?
So here's the point. If I store n plus k, if I store n plus k bit patterns, then those n plus k patterns can have different values for the first 10 bits.
Right.
So you can end up storing up to n plus k patterns even for the first 10 bits. Right? For n bits, I have 2 raised to n possible combinations, not just n. Right? So by appending stuff, I get a network with greater capacity, which means that of these 2 raised to n, I can store a greater number.
Okay.
Right? That's all it is. But again, it's convenient to think of it as a probability distribution, and this is the more common interpretation of Boltzmann machines. So overall, if I gave you a partial pattern, even for the visible unit, so let's say I gave you those 3 bits and I told you I don't know these 2 black bits. What I could do is just fix those 3 bits later on and then use the same update rule, the stochastic update rule, to let the entire network evolve and eventually sample over a sequence, the final stabilized sequence, to read off the unknown bits. You can do this for filling out patterns. You can do this for denoising patterns. You can do this for computing conditional probabilities of patterns and even classification. So how would you use this machine? We've defined hopfield networks. We've defined the probabilistic version of the hopfield networks. How would you use these networks for classification, right? How can I use this as a classifier? For this, observe that when I'm sampling the S1, so when I have partial patterns and I fix 1 bit and let the network evolve to compute the rest of the bits, what I'm really doing is performing this guy, right? I'm computing argmax, or the expected value of S1 given S2. So if I were performing classification, what could I do? I could have these bits represent features. And these bits could be a one-hot representation of class. And my training samples are going to be a combination of the features in the class. And then I train my Boltzmann machine. Later, when I get my test data, I can say that the class portion of the network is obscured. So those black covered boxes are the bits that represent the class. And then I can let the network evolve. And then I could read off the class, right?
So we initialize the class portion randomly?
Yeah. And then let the whole thing evolve, right? And you would repeat this many times just to get a very robust estimate, right? So basically, given features, you anchor the features, estimate the a posteriori probability of the classes over many runs, and choose the most likely class. So it kind of, this very simple idea ends up looking very powerful when you begin thinking of how you can actually use it. But the real power comes from something else, which I'm going to spend less than 8 minutes on, right? Training takes forever, doesn't really work for large problems. You get a small number of training instances over a large number of bits, right? And here's where, so Boltzmann machines were never really very popular until somebody realized that you can solve a lot of the problems by getting rid of some of the connections. So in the standard Boltzmann machine, every neuron connected to every other neuron, right? But once I begin extending these patterns to have visible and hidden neurons, I can separate the 2 components out and say that the visible bits don't talk to one another and the hidden bits don't talk to one another. So now I make a bipartite graph where all the hidden bits talk to all the visible bits and all the visible bits talk to all the hidden bits. This is what's called this was originally called a harmonium model by Paul Smolinski back in the early 80s, I think. And Hinton basically renamed it, or someone downstream renamed it as the restricted Boltzmann machine. Yeah?
So other than the bidirection, how is that different?
Nothing different. It's a standard Boltzmann machine. I've just made it bipartite.
It looks like a feed forward.
It looks like a feed
Yeah, I mean, like, other than the bidirectional, how is that different from just like a neural network?
So how it is different is that the value A, so if I fix the input, it's a standard neural network. And so this is exactly how you can think of your standard MLP as just a mean field estimate from your standard MLP. How it really differs is in that the gray boxes can go back and affect the input. So you're absolutely right. And this is exactly why the RBMs came back and became very popular, because people began using it to initialize neural networks. And you'll see that the popularity shot up in the early 2000s when Hinton's group showed that if I thought of my standard MLP as an RBM and then use those to learn my weights, and then I initialize the weights for my eventual MLP using those values, then the network converged to actually reasonable solutions. Whereas for the past 20 years, MLPs, nobody had successfully managed to actually train an MLP for any real task. So the new revolution in neural networks.
To use this machine to visualize the weights.
Yeah.
Can it do with multiple perceptions?
So this is, yeah, so you
This
can.
is one hidden layer, right?
You can keep adding layers. So I'll have a few minutes. So let me go through this, right? But here's what you would do this. Here's what you would do. So here is the key piece, right? Now sampling becomes a very trivial thing. If I give you some visible patterns, you're only going to sample the hidden patterns. And there's no looping because everything is sampled only once, right? The hidden patterns don't talk to one another. And then if I give you the hidden patterns in a single loop over the visible patterns, I get a sample over the visible patterns. The visible patterns don't affect each other except through the hidden patterns. And so you get this very interesting switching behavior where I can fix the visible patterns and sample the hidden patterns, fix the hidden patterns and sample the visible patterns. And so remember, in the full Boltzmann machine, what we did was we fixed the visible patterns, then we had to iterate several times to actually learn the extensions, the hidden values, and then we got many, many samples of the hidden values, and then we had to unclamp it and repeat the whole process. That becomes greatly simplified. Over here, when I give you a visible pattern, there's no looping. In one sampling shot, you have extended it with the hidden values. So and then here was the second step, where again there was this very complicated evolution where the entire network evolved all at once. Here, if I want to do the unclamping, I fix the hidden values, fix the visible values, sample the hidden values, fix the hidden values, sample the visible values, and so on. So here's what you would get. So I could start off by initializing, if I have some training instance, I would initialize the visible patterns with the training instance, sample the hidden values, and then from the hidden values I'd sample the visible values. I can go back and forth, right? And in theory I have to go all the way to infinity to actually get things to work properly. But then if I did so, updating the weights is very easy, right? So for the first term in the gradient descent rule, you just needed that product on the extreme left, the arrow to the extreme left. For the second term, you needed all of the arrows. You summed over all of the arrows. And that's what you would have got. But again, remember, in a hopfield network, we said it was sufficient to just raise a neighborhood, right? That really means that it turns out that you can just do this one single step. This was the famous contrastive divergence algorithm, where I start off with a visible pattern, compute the hidden pattern, then compute the visible pattern from it, and compute the hidden pattern from it. And then I can just learn the correction terms, the update terms, from just this 3-step update. And it still gives me a perfectly good estimate for the gradients to be updated. So these, it turns out, are excellent models for binary or binarized data and can be extended to continuous valued data. And they're useful for classification and regression. The most common use is for pre-training models. So I'm actually going to sort of, since we're running out of time, I'll sort of quickly give you a glimpse of how these things work. If you have, now these things can be extended to continuous valued models, and the way they would do it is you can just attach a Gaussian to every visible unit, and now you have where the parameters of the Gaussian, the mean and the variance, could be learned, and then you get this restricted Boltzmann machine, which is a very complex generative model, but yet very simple in its structure. Or now you can also extend them to have many layers. So instead of just one layer, what can I do? I can just think of this whole thing as this very deep structure. This is a deep Boltzmann machine. And the deep Boltzmann machine you can think of as having many restricted Boltzmann machines connected one to the other. So if I have the lowest guy stabilized, then I can use the patterns from that guy to learn the next layer and work my way up. And this gives me a very complex machine with lots of interactions. And they require somewhat more detailed algorithms to train. Now, fact of the matter is, in theory, these things are very cute. In practice, they're not very popular because of the obvious nature, right? Now, I have actually skipped a bunch of topics. I'm not going to go over those. But the key point is where RBMs became popular is that RBMs really became popular as a mechanism for pre-training networks, in the sense that instead of just saying, now if you think of it this way, right? If I give you an input, visible patterns, and then I train I sample the hidden values, and then go back and sample the input values. This one way of explaining this is as a restricted Boltzmann machine. There's a different way of explaining it. We call it an autoencoder, right? And so there was a lot of, so while a lot of the initial work tried to view this as stochastic machines, there was a second line who just said, you can train these autoencoders. And if you learn autoencoders and then initialize the weights of the network with the corresponding weights, you get very good initial estimates. That turned out to be true as well. So there are more structured DBMs, and that whole area has kind of blown up in spite of its relative lack of popularity. The framework itself is extremely powerful. The idea behind the previous 3 lectures is to just give you some kind of an intuition, some kind of the groundwork that you can use to go off and read additional papers and not get too confounded by the math. It's very important to be able to devolve the whole thing down to something simple like a hopfield network to see what really is happening underneath. But this is about all we're going to talk about it. I'll stop you. Any questions? Yes?
Is the distribution still a Boltzmann distribution once you have a deep network?
It's not a conventional Boltzmann distribution, but at each layer it is going to be, right?
Okay.
Yeah.
I was just wondering what kind of things you can model with that.
So you can think of, because you're really saying that you can, if you make it, simply making it deep doesn't buy you very much. Simply because you can think of a deep network with many neurons as just having an exponentially large hidden layer. Where it actually ends up being powerful is by being able to impose priors elsewhere in the network, in the deeper layers, which actually gives you a lot more control and a lot more structure to the distributions learned. And so that's more of the nature in which these things are learned. Yeah.
Is there any real applications that's being used, like text or image? Because I've never seen this as part of any signal wires.
Oh, there's that. So not lately, but if you actually go back just a few years.
Okay, so not lately.
Yeah, no, they're not, but you can still find a lot of papers on the topic. And right. Thanks, everybody.